Think about how your spam filter somehow knows what to junk and what to let through. Or maybe you've glanced at a stock chart, trying to figure out the next move.
Yeah.
Even just checking the weather forecast relies on it. What's the underlying similarity? Well, it's all about data, and the tricky part is that data is constantly in motion. The patterns we see today might, completely shift tomorrow.
That's a really crucial point. And this brings us to a fascinating challenge in the world of machine learning called concept drift. It pops up, well, everywhere.
Everywhere.
Like your spam filter learning new tricks from the spammers, fraud detection systems adapting to the latest scams. Even things like predicting traffic or monitoring forests have to deal with these changing data patterns. The fundamental rules that govern the data, the underlying distribution, they aren't fixed. They evolve, often in pretty unexpected ways.
Okay, concept drift. It sounds like this isn't just one type of change we're talking about then.
Precisely. No, researchers have generally identified 4 main ways this happens. First, there's abrupt drift.
Abrupt. Like a sudden switch.
Exactly. The data patterns change almost instantly to something new. Then you have gradual drift, where the change happens more slowly. You get a mix of the old and new before it settles on the new pattern.
Okay.
Then incremental drift is kind of like a series of smaller shifts, where the data goes through maybe a few unstable phases before landing on a new stable state.
Right. And the last one.
And lastly, there's recurrent drift. That's where a past data pattern reappears after being different for a while, like an old trend coming back.
So if the data is always morphing like this, how do our machine learning models keep up? It feels like they'd always be maybe one step behind.
That's exactly the core challenge.
Yeah.
Most machine learning models are trained on a static snapshot of data, assuming those patterns will stick around.
Right.
So when concept drift happens, the model's accuracy can really take a hit because it's operating based on, outdated information.
Which leads us nicely to the intriguing research you shared. This paper looks at a new way to tackle this very problem, this concept drift, especially when dealing with streams of data.
Yes, exactly. The paper introduces an approach called EACD. It stands for Evolutionary Adaptation to Concept Drifts.
EACD.
And what makes it particularly interesting, I think, is that it uses ideas inspired by evolutionary algorithms to adapt to these shifting data landscapes.
Evolutionary algorithms. That's about mimicking natural selection, right? Survival of the fittest, that kind of thing.
Basically, yes.
Yep.
And EACD is an ensemble learning method.
Right. We've talked about ensemble learning before. It's like getting a consensus from multiple experts, or multiple models in this case, rather than relying on just one. Leads to a more reliable prediction generally.
Exactly. And in a dynamic environment, with concept drift happening, this ensemble approach can be really powerful. You can adapt the team of experts over time.
So bringing in new ones, phasing out the ones that aren't relevant anymore.
Precisely. EACD uses these evolutionary algorithms to manage this team in a way that's designed to be particularly good at responding to different kinds of concept drift.
Okay, so our goal for this deep dive is to kind of unpack how EACD works under the hood and figure out why the researchers think it might have an edge over the methods that were already out there.
That's the plan. Understand the mechanism and its potential advantages.
All right, so we get why dealing with these data changes is so important. Before this EACD approach, what were researchers doing? What were the existing methods? It sounds like there were different ways of thinking about it.
Absolutely. The researchers broadly categorized existing ensemble methods into 2 main groups. You've got explicit methods and implicit methods.
Explicit and implicit. Okay, what's the difference?
Well, explicit methods are characterized by having a specific built-in way to detect when a concept drift has happened.
Like an alarm system.
Sort of, yeah. And then they react fairly quickly to that detection. Implicit methods, on the other hand, don't have a dedicated drift detector.
No.
Right. Instead, they adapt more gradually to changes in the data stream. They continuously update their ensemble based on the newest information. Think of it like slowly adjusting a thermostat based on the overall temperature, rather than waiting for a sudden spike or drop.
Okay, so explicit is like hitting the alarm button, taking immediate action. Implicit is more of a steady, ongoing adjustment. Can you give us a few examples of these implicit methods?
Certainly. The paper mentions several. There's online bagging, sometimes called OZABag.
OZABag, okay.
Which is like taking multiple slightly different samples of the incoming data to train each of your individual learners. Then there's online boosting, or OZABoost.
Boosting. That focuses on the mistakes, right?
Exactly. It sequentially trains the learners, focusing more on the examples the previous learners got wrong. Other examples include dynamic weighted majority or DWM,
TWM.
which adjusts how much weight or importance we give to each learner based on how well they're performing. It can even bring in new learners if the whole team is struggling.
Makes sense.
There's also the Accuracy Updated Ensemble, AUE, and its online version, OAUE, which constantly refine and weight the learners based on their recent accuracy. And finally, methods like ADACC, Anticipative Dynamic Adaptation to Concept Changes. It tries to stay stable by kind of anticipating when changes might be coming.
Yeah.
And SAE, this Social Adaptive Ensemble, which organizes learners in a sort of network.
Wow, that's quite a few. But it sounds like these implicit methods, they share a common weak spot.
Exactly, that's what the paper points out.
Yeah.
The main drawback is that they often adapt rather slowly to new concepts because they're designed for that gradual change.
Okay.
Plus, since they don't have a specific drift detector, these changes aren't usually identified right away. There's a delay.
Right, that makes sense. Slow reaction time. So what about the explicit methods, the ones with the alarm button? How do they work?
So explicit methods incorporate a mechanism to specifically detect when a concept drift occurs. When that alarm goes off, they take more immediate action.
Like what kind of action?
Like readjusting the importance of different learners. Maybe getting rid of older learners or bringing in entirely new ones trained on the newer data.
Gotcha. Examples.
Examples they mention include adaptive boosting, or a boost. It resets learner importance when a drift is detected. Then adwin bagging, or adwin bag, which combines online sampling with a drift detector called ADWIN to decide when to create new learners.
ADWN, that's the detector part.
Yes. Leveraging bagging, or LevBag, builds on adwin bag by adding even more randomness. Recurring concept drift, or CD, uses a memory bank to store past patterns and tries to reuse old learners if a drift reappears.
Oh, interesting, like bringing back an old expert.
Kinda, yeah. And finally, adaptive random forest, or ARF. That's a version of the popular random forest technique where each individual tree in the forest has its own drift detection mechanism.
So each tree can sense change independently.
Exactly, allowing trees to be replaced if a change is suspected for that specific tree.
It sounds like these explicit methods are more on the ball then, quicker to react. But the paper also mentions a potential problem here too.
Yes. The main issue highlighted is that they can be quite sensitive to false alarms.
False alarms, like mistaking random noise for a real change.
Precisely. Or just, temporary fluctuations in the data. If a drift is incorrectly detected, it can lead to unnecessary changes in the learning system, which might actually hurt its accuracy.
Right, overreacting.
Exactly. And on top of that, designing a really good drift detection mechanism that can reliably spot all those different types of drift we talked about, abrupt, gradual, incremental, recurrent. That's a really tricky challenge in itself.
So it sounds like a classic trade-off. Implicit methods are stable but maybe slow to react, while explicit methods are quick but potentially a bit jumpy or easily fooled.
That sums it up pretty well.
And this is where EACD steps in, aiming to get the best of both worlds. Is that the idea?
Precisely. The researchers propose ECD as a new ensemble learning method that tries to blend the strengths of both these approaches, hoping to get that faster adaptation without being overly sensitive.
Okay, so how does EACD actually do this? What are the key ideas behind its approach? Left that into the weeds a bit.
Okay. The central idea of EACD involves using random feature selection. So, choosing different characteristics of the data to create a diverse set of what they call classification types within its learning team.
Classification types.
Right.
Like different perspectives on the data.
Yeah. And then it uses two different evolutionary processes, something called replicator dynamics and a genetic algorithm, to adapt these types to concept drifts.
Two evolutionary processes. Okay, that sounds pretty sophisticated. Can you walk us through how EACD is structured? You mentioned layers.
Certainly. EACD has a two-layered structure. There's a base layer and a genetic layer.
Base and genetic.
Right. Both layers are made up of a collection of individual learners' decision trees, in this case, that independently make predictions on new data. However, the base layer is always active, constantly working.
Always on.
Always on. While the genetic layer only kicks in after the genetic algorithm has run and its classification types are considered, ready to go or mature.
Okay, and there's a difference in how much they influence the final decision.
Yes. Importantly, the learners in the genetic layer are given more weight in the final overall prediction compared to those in the base layer. In the paper, they use a weight of 2 for genetic, 1 for base.
So the genetic layer's opinion counts for more, reflecting its more optimized nature.
Exactly. It's seen as the more refined part of the system.
Okay, let's start with this base layer then. How is it set up and how does it adapt to changes?
All right. The base layer begins by randomly selecting a certain percentage, let's call it P, of all the available features in the data stream.
Just a random subset of features.
Yep. This random selection creates what the paper calls a classification type, essentially, a focus on a specific subset of features. This process is repeated many times, creating independent classification types.
So you get different random views of the data?
Correct. And for each of these types, decision tree models are built using the initial chunks of incoming data. This initial training gives each type a foundational understanding based on its specific view.
Okay, so we have these different classification types, each with its own set of decision trees, looking at different slices of the data. How does the base layer then evolve as new data keeps coming in?
This is where replicator dynamics, or RD, comes into play.
Replicator dynamics sounds like something out of biology.
It is. It's a concept from evolutionary game theory. Think of each classification type as a different strategy in a game.
Okay.
And its payoff is how accurate the decision trees within that type are on the most recent data block.
So better accuracy means higher payoff.
Exactly. RD works on the principle that strategies performing better than the average payoff tend to become more prevalent, while those performing poorly become less common.
Survival of the fittest again.
Pretty much. In our case, this means that classification types that are doing a good job predicting get a new decision tree added to their collection.
They grow stronger.
Right. And poorly performing types, they lose a tree.
They shrink.
Okay. And this is a continuous cycle. Classify new data, evaluate accuracy for each type, calculate the average payoff, apply RD to grow or shrink the number of trees in each type based on that average, and then retrain all the trees with the very latest batch of data.
Wow, okay. Constantly adjusting. Are there limits? Can one type just take over?
Good question. Yes, there are limits. Upper and lower bounds on the number of trees each type can have. This keeps the overall size of the ensemble manageable and prevents any single type from totally dominating or disappearing completely.
So it maintains diversity while rewarding success.
Exactly. In essence, the base layer is like a constantly evolving team where the most effective players, the best types, get more resources, more trees. It provides this smooth, continuous adaptation.
That sounds like a really interesting way to get that implicit gradual adjustment. Now let's talk about the second layer, the genetic layer. How does that build upon what the base layer is doing?
Okay, so the genetic layer takes the classification types that were created in the base layer as its starting point. They become the initial population for a genetic algorithm, or GA.
Ah, the other evolutionary process.
Right. The main goal here is to further refine and optimize the specific combinations of features that each classification type is focusing on. It's trying to find even better feature subsets.
How does it do that?
The GA works with a small buffer of the most recently seen and labeled data. This buffer acts as its training ground, its environment for selection.
So it looks at recent performance.
Yes. Think of the genetic layer as a focused optimization lab, constantly trying to improve the feature combinations discovered by the broader, more exploratory base layer.
So the GA is essentially trying to find even better subsets of features within those already randomly selected ones. What are the steps involved in this optimization? How does the GA actually work?
Okay, the GA operates in a series of key steps, like a cycle. First, there's selection.
Selection. Choosing the best ones.
Pretty much. The classification types that have shown better accuracy on the recent data in that buffer are chosen to move on. Their accuracy is their fitness.
Okay, survival of the fittest types. What's next?
Next comes crossover. This is where the selected high-performing types essentially breed.
Breed.
Yeah, they create new classification types called offspring by combining their sets of features, like mixing the traits of successful parents.
Okay, combining the good bits.
Hopefully. Then, after crossover, there's mutation.
Mutation. Random changes.
Exactly. There's a small chance the paper used around 5% that an offspring will get a completely random feature instead of one inherited from its parents.
Why do that?
It introduces new possibilities, injects novelty, and helps the algorithm explore a wider range of feature combinations, avoiding getting stuck in local optimum.
Ah, prevents it from getting too narrow-minded.
Right. So this cycle of selection, crossover, and mutation repeats for a set number of generations, say G times.
And after G generations?
Once these generations are complete, the resulting set of optimized classification types forms the new genetic layer. These are the refined, evolved feature combinations.
And these optimized types in the genetic layer have a bigger say in the final prediction you mentioned.
Exactly. As we said, the predictions from the learners in this genetic layer get a higher weight 2 versus weight 1 for the base layer.
So they have a stronger influence.
A stronger influence on the final overall prediction, yes. But remember, this genetic layer isn't always active.
Right, it has to be mature. What does that mean again?
It's considered ready or mature and only starts contributing to the final predictions when its performance on the most recent data is actually better than the average performance of the entire EACD system up to that point.
Okay, so it has to prove itself first before it gets that extra weight.
Exactly. It ensures the optimization process actually resulted in an improvement before letting it strongly influence the output.
Okay, so the genetic layer provides this more targeted optimization. But how does the system know when it's time to re-optimize these feature combinations? You can't just run the GA once, right? When does it get to run again?
Good point. No, it needs to adapt. The paper proposes two ways for this re-optimization or restarting of the genetic algorithm to happen: an implicit way and an explicit way.
Implicit and explicit again. Okay, tell me about the implicit way first.
Okay, in the implicit mechanism, the GA restarts basically when the base layer starts outperforming the genetic layer.
Oh, interesting. How do they measure that?
They look at the average accuracy over a recent window the paper used the last 10 data blocks. If the base layer's average accuracy becomes better than the genetic layer's average accuracy over that window,
Then it triggers a rerun of the GA.
Exactly. The thinking is this suggests the base layer might be adapting more effectively to a new underlying data pattern on its own, so it's a good time to re-optimize the genetic layer based on this potentially new direction captured by the base layer.
That's a clever way to detect a possible need for re-optimization without explicitly looking for a drift signal. What about the explicit way? That must use a drift detector.
Correct. The explicit way relies on using a dedicated method to detect concept drift. In their work, the researchers use something called EDDM.
EDDM, Early Drift Detection Method.
That's the one. EDDM specifically looks at the pattern of errors, like the distance between misclassifications, to try and identify potential drifts. It's known for being pretty sensitive to gradual changes.
Okay, so how does EDDM trigger the GA?
In this explicit approach, EDDM has two levels: a warning level and a drift level. When EDDM first gives a warning that a drift might be occurring,
Like smoke before the fire.
exactly, that's when the buffer of data for the genetic algorithm starts filling up with the incoming data points.
Okay, starts collecting evidence.
Right. Then, if EDDM later confirms that a drift has indeed happened, hits the drift level the GA is triggered, it then rebuilds its layer using the data that has accumulated in the buffer since the warning.
And that buffer now represents the new data pattern, hopefully.
That's the idea. It uses data collected during the suspected transition phase to optimize for the new concept.
So the explicit method uses a specific alarm, EDDM, to say, hey, things are changing, and then kicks off the re-optimization using recent data, while the implicit method uses the relative performance of the two layers as its trigger. What's the thinking behind having these two different approaches within EACD? Why not just pick one?
Well, the reasoning, as the researchers explain it, goes back to trying to combine the strengths and mitigate the weaknesses of purely implicit and purely explicit methods that we talked about earlier.
Okay, bringing it back to that trade-off.
Exactly. The replicator dynamics in the base layer provides that continuous smooth adaptation, the implicit part. This helps avoid the slow reaction times you sometimes see in purely implicit systems.
Right, keeps things moving.
On the other hand, the genetic algorithm in the genetic layer, especially when it's triggered by a drift detector like EDDM in the explicit version.
The EACDX version.
Right, EACDX. That allows for a more immediate and focused reaction to identify concept drifts, and it provides that targeted optimization of the feature combinations.
So that tackles the slowness of implicit methods.
Correct. And by having the stable base layer adapting continuously with RD, it might also reduce the sensitivity to false alarms that can sometimes plague purely explicit methods. The GA optimization only happens when there's stronger evidence of change, either relative performance shift or explicit detection.
So the base layer acts as a kind of buffer or first responder.
In a way, yes. It's providing continuous adaptation, while the GA provides periodic, more intense optimization when needed. It's really an attempt to get the responsiveness of explicit methods with the stability of implicit ones, all within a single system.
That makes a lot of sense, a sort of layered defense against concept drift. Okay, theory sounds good. Now, how did the researchers actually put EACD to the test? What kind of experiments did they run?
They performed a really thorough set of experiments, which is great to see. They used both artificially generated data streams and real-world data streams.
Both synthetic and real data. Nice. What kind?
For the artificial data, they used 4 well-known data generators: SEA, Hyperplane, Random Tree, and LED.
Ah, the usual suspects for testing drift algorithms.
Exactly. Each one is designed to simulate different types of concept drifts, abrupt, gradual, recurring changes. And they didn't just use the standard versions. They created 10 different variations for each generator by tweaking the settings.
Really trying to challenge the algorithms.
Definitely. And for real-world data, they used 5 datasets: forest cover type, electricity, airlines, poker hand, and the KDD Cup 99 dataset. Yeah. Each with its own unique characteristics and presumably its own types of inherent concept drift.
Okay, a good mix of data. And how did they measure performance? Who did they compare EACD against?
They compared EACD against several of the leading ensemble methods for classifying data streams that we discussed earlier.
Like DWM, left bag.
Yep, exactly. Dynamic weighted majority, DWM, online accuracy, updated ensemble, OAUE, OS boost, leveraging bagging, left bag, and adaptive random forest, ARF. Quite a strong lineup.
And the evaluation metric? Accuracy?
Primarily accuracy, yes.
Yeah.
They use 2 main ways of evaluating performance over the stream: immediate and delayed prequential evaluation.
Prequential. That's like testing on data as it arrives, right? Predicting the next thing.
Precisely. Immediate evaluation means the true answer, the label, for each data point is available right after the algorithm makes its prediction, so it gets immediate feedback.
Okay.
And delayed? Delayed evaluation is more like many real-world scenarios where there's a time lag in getting the correct answer. You make a prediction, but only find out if it was right much later.
Like credit fraud detection, maybe?
Could be, yeah. In their experiments, they set a delay of 1,000 data points. They tracked how the classification accuracy changed over time for both scenarios, and also measured how much computing time each method took.
Time is important, too. Did they test different versions of EACD itself?
They did. They tested versions that only used the base layer, and then the full EACD with both implicit and explicit genetic layer triggers, sometimes with different parameter settings for things like the GA. It was quite comprehensive.
So, after all that testing, what were the key findings? Did EACD deliver on its potential? Did it manage to get the best of both worlds?
The results were quite encouraging, generally speaking. The researchers found that the explicit version of EACD, the one they called EACDX.
The one using ADDM for the trigger.
Right. That version generally achieved the best average accuracy across many of the datasets. And this held true in both the immediate and the delayed evaluation scenarios.
That's pretty strong. Better average accuracy across many datasets and evaluation types.
Yes. It consistently performed well on datasets that exhibited various kinds of concept drifts, those sudden abrupt changes, the slower gradual shifts, and those recurring patterns. They saw this clearly in their detailed analysis of the SEA data generator results.
Okay, that sounds like a pretty significant result then. High accuracy in diverse, changing environments. Were there any downsides or trade-offs? No free lunch, usually.
True. There was a noticeable trade-off when it came to computational time.
Ah, okay, it was slower.
Yes. The time it took to evaluate EACD, especially the versions that included the genetic layer, and particularly the explicit version EACDX that also used the drift detection. That time was often longer compared to some of the other methods like, say, DWM and OS boost.
Which makes sense, right? Running 2 evolutionary algorithms plus a drift detector sounds computationally heavier.
It is. That complexity comes at a cost. The paper also points out something important about statistical significance.
Oh, what was that?
They ran statistical tests, Friedman anemone tests, to see if the accuracy differences were truly significant. They found that while EACD's accuracy was statistically significantly different from some methods, like DWM and OS boost, it was not statistically significantly different from others, namely LevBag, ARF, and OAUE, based on those tests.
Wow. Okay. So while it often had the best average accuracy, the difference compared to some other top contenders wasn't large enough to be statistically definitive in all cases.
Exactly. It's an important nuance. Strong performance, often leading, but maybe not always head and shoulders above all the other state-of-the-art methods in a statistically strict sense.
That's an important detail. So strong accuracy, potentially class-leading, but with a higher computational cost sometimes, and not always statistically beating every other top method. Did they gain any interesting insights by looking at how EACD handled specific types of drifts? You mentioned the SEA generator.
Absolutely. That's where looking at the synthetic data really helps. When they look closely at the results on the SEA generator, which has those controlled, abrupt, gradual, and recurrent drifts,
What did they see?
they observed that both EACDEX and ARF, adaptive random forest, were good at responding quickly to those sudden, abrupt concept changes. They reacted fast.
Okay, good for sudden shifts. What about the other types?
Interestingly, ECDX seemed to adapt particularly well to recurrent concept drifts. It was quick to regain its accuracy when a data pattern that had appeared before came back again.
That's valuable. And gradual drifts, those can be tricky.
They are. And EACDX showed a robust ability to handle gradual concept drifts too. The researchers suggest this might be due to that two-stage adaptation process we discussed.
The RD in the base layer plus the GA in the genetic layer.
Exactly. The continuous, smoother adjustment from replicator dynamics in the base layer handles the initial slow change, and then the more targeted optimization by the genetic algorithm, especially after an explicit detection, helps it lock onto the new pattern more firmly.
So the combination helps it manage those slow transitions effectively.
That seems to be the thinking. That combination appears key to its adaptability across different drift types: abrupt, recurrent, and gradual.
That two-stage process does sound crucial for its flexibility then. So to kind of sum it up, it seems EACD, especially that explicit version, EACDX, offers a genuinely promising new way to deal with the constant changes we see in data streams. It achieves high accuracy in a variety of situations, even if there's that computational cost.
That's really the key takeaway, I think. The explicit version of EACD demonstrated strong capabilities in adapting to different types of concept drifts and achieving high accuracy in these dynamic environments.
Yeah.
And while the increased computational cost is definitely something to consider, its performance in terms of accuracy suggests it could be a really valuable tool in applications, where keeping up with changing data patterns is absolutely essential.
And it sounds like the researchers themselves aren't done yet. They have ideas about how they might improve EACD even further. What kind of future work did they suggest in the paper?
They did, yes. They outlined several interesting directions for future research. Quite a few, actually.
Like what?
Well, one idea is to develop a way to automatically prune or remove classification types that consistently don't perform well over a long time. Deadweight removal, essentially.
Makes sense. Streamline the ensemble.
Another suggestion is to use dynamic weights for the base and genetic layers instead of the fixed 1 and 2 they used. Maybe the optimal balance changes over time.
Adaptive weighting. Interesting.
They also proposed looking at different strategies for removing decision trees within a classification type when it hits its upper limit. Instead of just removing the worst performing one, maybe remove the oldest one, for instance.
Exploring different replacement strategies.
Okay. And for efficiency, they suggested exploring integrating well-performing types from the genetic layer back into the base layer after a while.
Oh, so if the GA finds a really good combination, make it part of the permanent team.
Sort of, yeah. Especially since the genetic layer might get reset periodically anyway, it could preserve good discoveries. They also considered developing a kind of pattern recognition system.
For what?
To track how useful different classification types are across various environments or contexts. This could be particularly helpful for dealing with those recurring concept drifts, recognizing when a previously useful type might be relevant again.
Smarter reuse of components.
Exactly. And finally, a really interesting one. They even proposed investigating whether the behavior of the classification types themselves, how their populations change via RD, maybe could be used as the basis for a completely new type of concept drift detection system.
Wow, using the system's own adaptation dynamics to detect drift. That's meta.
It is. Lots of potential avenues there.
Those all sound like really promising directions for future development. It's fascinating, isn't it, to see how these adaptive learning systems are evolving, trying to keep pace with our ever-changing world.
It truly is. It makes you think about just how much of the data we encounter every single day. I mean, from the news we read online, the recommendations we get, to the smart devices we use is constantly shifting and evolving under the surface.
Yeah, it's everywhere.
And systems that can intelligently adapt to these changes, like the EACD approach we've explored in this deep dive, they have the potential to become increasingly vital. Just indispensable, really, in a huge range of applications.
Providing more accurate predictions, better understanding.
Exactly. A better understanding of the world around us as it continues to change. Perhaps this discussion might even spark some thoughts for our listeners about the dynamic nature of data in their own fields or areas of interest, and maybe the potential impact or even the necessity of these kinds of adaptive learning systems going forward. What happens when the rate of change itself starts changing?